So the question now arises is, how is nuclear magnetism generated? What is its basis? And we will here talk about the classical view, more on a classical view than the strict quantum mechanical view, but I will make some references to the underlying quantum mechanical theory. Now, it is known from nuclear physics that a nucleus typically has an angular momentum, which we know from our physics classes is denoted L, but here it is called P. So we can envisage we have the nucleus here, and the nucleus has an angular momentum. Now, we have with an angular momentum, classically, now we'll take here the classical view, classically we associate with an angular momentum a rotating motion. So we have a rotating motion, and we'll stick with the classical view because this gives us an intuitive feeling where the magnetism comes from. So if we feel like, in the description, that the nucleus is rotating, since the nucleus is positively charged, there is a rotation of the electrical charge. As you can imagine, this is like the Earth, it's positively charged, it's rotating, so at the equator the charge is moving, and moving charge implies a current. So, here is the angular momentum, and since we have a rotating current, here's the rotating current, so we'll associate this with a rotating current, and such a rotating current now is associated with a dipole moment. It's just like a current. This is again the classical picture. It's not perfect, but it helps us understand where nuclear magnetism comes from. So we'll associate it with, just like with a ring current, with a dipole moment mu, that we will call mu here. Now, in terms of magnetism, we can picture the nucleus as if it was a bar magnet. The magnetism of the nucleus acts as if it is a bar magnet. It's not a bar magnet per se, but it acts electromagnetically like a bar magnet. It has a dipole magnetic field associated with it. So that's the intuitive reason why with some nuclei we have an angular momentum. Once we have an angular momentum, we have with it associated a dipole moment. Now, if we look at a magnetic moment of an individual spin in a induction field, so this dipole moment, this magnetic moment, is given by mu is equals to gamma times the angular momentum. And gamma here is called the gyromagnetic ratio. It's an empirical constant. There's a more profound theory behind it on what dictates the gyromagnetic ratio for a given nucleus, but we'll here, for our intents and purposes, it suffices to say that this is an empirical constant. Now, what we know from quantum mechanics is that the angular momentum of a nucleus is quantized. So it has, for the z component of the angular momentum, it has 2i plus 1 values, and they take on the values mi. So here is, for example, where I can go from minus the angular momentum, the z component, the quantum number m here, can go from minus I to plus I and increments in values of 1. So here in this particular example, we go from minus 3 halves to minus 1 half, plus 1 half, plus 3 halves. That's the z component of the angular momentum. We can calculate the total angular momentum, and this is given by this equation here. So it's the quantum number, the angular momentum number here, I times I plus 1 times h over 2 pi. So if we take this for a spin 1 half, so the spin 1 half can take the values 1 half and minus 1 half the angular momentum. In this case, the total angular momentum is times the Boltzmann constant times square root of 3 over 4 pi. That we can verify by putting here into I 1 half. So that's for a spin 1 half. So let's look at some isotopes and their gyromagnetic ratio gamma. And first, we want to introduce some isotopes that do not carry an angular momentum. Those are carbon-12, oxygen-16, etc. They have typically even mass and even atomic number. So they don't carry a nuclear spin, they don't carry a nuclear angular momentum. Then we have nuclei with spin 1/2. These are the proton, the hydrogen nucleus, H1, C13, and nitrogen 15. Another one is phosphorus 31. They are characterized by a spherical charge distribution in the nucleus. And then we have the spins that are larger than spin 1/2. Deuterium is an example, boron 11, sodium 23, lithium 6 is another one, lithium 7, etc. Depending on whether they have odd or even mass and an odd atomic number, they carry either half integers, so they're 3 halves, 5 halves, etc., or the whole integer, their spin 1, 2, 3, etc. What's particular about these nuclei is that they have an ellipsoidal charge distribution. They generate within the nucleus an electric field, and it's a so-called quadrupolar electrical field. They have distinct different properties typically than the spin 1/2. Now let's look at some examples here. So we have the isotope listed, we have the spin, whether it's spin 1/2, etc., the gyromagnetic ratio, and here we list the gyromagnetic ratio not as the gyromagnetic ratio, but we divide it by 2 pi, so this gives us a number that relates the Larmor frequency to the the frequency to the Teslas. And finally we have the abundance. So what do we see here? We have hydrogen spin 1/2, gyromagnetic ratio is 42 megahertz per Tesla, and it's basically every hydrogen atom is a H1. Then we have deuterium. This has a spin 1, so it's a quadrupolar nucleus, very low gyromagnetic ratio, and the abundance is about 100%. Phosphorus 30